All right, shall we start? So, good afternoon, everyone. I am very glad to be here to present this talk about reproducible performance evaluation of different OpenStack deployments using our framework, which is called EnOS. So EnOS has been part of the action accomplished by the Fog Edge and massively distributed cloud special interest group, and has been mainly developed by academics people listed in this slide, who are people from the Discovery Initiative at INRIA. So my name is Dimitri Pertin. I am a researcher at INRIA, the French Research Institute of Computer Science and Automation. I am involved in the Discovery Initiative, which is an ambitious project about building a fully decentralized cloud manager. And more precisely, my topic in this project is about the deployment and the reconfiguration of cloud applications on top of massively distributed infrastructures like fog infrastructures. So naturally, I am involved in the FEMDC, Fog Edge and Massively Distributed Cloud SIG, and I am a contributor of EnOS, which is a framework that I'm going to present in this talk. So this is the agenda of the talk. I'm going to first give an introduction of the Discovery project and our implication in the FEMDC SIG in order to understand the context that motivated us to develop EnOS. Then I will present an overview of performance evaluation to fully understand what are the challenges addressed by EnOS. And we'll see in the third part the presentation of the framework and how it solves these challenges. I will then illustrate some EnOS use cases before the conclusion. So first, let me introduce the vision of the Discovery Initiative. The Discovery is a project that deals with the context of fog infrastructures, which are a new form of cloud infrastructure, but rather than managing large centralized data centers, it involves the management of many micro data centers, which cooperate in order to provide cloud computing features. So what motivated us is that point of presence, POP, are communication facilities that typically hold servers and routers at the edge of the network backbone. POPs are good candidates to hold micro data centers, the micro data centers that are required in a fog infrastructure. So the goal of the Discovery project is to build such a massively distributed cloud at the edge of the network. Such infrastructure offers a new paradigm called the fog computing. And the main reasons why we care about it remains in the 3 points depicted in this slide. So first, such infrastructure is reliable. So there is no point of failure. Indeed, if there is a micro data center that fails, you can still operate the system from any other micro data center. Such paradigm brings also governance, since POPs tends to be globally distributed. So for instance, if I run a company in Australia, I can request a compute node in Australia, in an Australian POP. So finally, as you can see on the picture, the fact that we deploy compute nodes at the edge of the network helps us to reduce the latency between end users and compute nodes, since they are geographically closer. So latency is indeed a critical metric for many applications emerging from the Internet of Things, like smart cars that cooperate in order to avoid collisions at crossroads, for example, or tactile internet, which provide the ability to deliver remote physical experiences. But maybe for more precise information about fog and edge computing, I encourage you to have a look at the numerous great talks that have been presented during this summit. Here is a motivating example of such infrastructure, which is the Renater network backbone. So Renater is the French National Research and Education Network, which is composed of 72 points of presence, which are interconnected by 10 gigabytes internet. And as you can see on the picture, each red point is a point of presence on which we want to deploy a micro data center. So the question is, how can we operate such a massively distributed cloud infrastructure? So to that end, we naturally turned to OpenStack, the de facto solution for managing cloud. And we founded the Fog and Edge Massively Distributed Cloud working group between Mitaka and the Newton release of OpenStack. So this group is now a SIG, and the goal of this SIG is to gather the OpenStack community around the question of how OpenStack can address Fog and Edge computing use cases. So we have indeed various ongoing actions, like providing an executive summary of Fog computing to the community. So it involves the definition of all the words around Fog computing, and the definition of use cases related to this area. We also involved into the evaluation of critical services in OpenStack, in the particular case of massively distributed deployments. And we also involved into evaluating some architectural choices around that. So if you want more information, I encourage you to have a look at the wiki or have a look at the RSC meeting of the FEMDC SIG. But as you can see, evaluation is a critical thing for us in order to understand bottlenecks and to validate the architectural choices around Fog computing, around OpenStack in the Fog computing context. So indeed, since OpenStack relies on a set of critical services like the database and the message bus, which are centralized, it can be a bottleneck for the special case of Fog computing. Furthermore, there are different ways to deploy OpenStack to address this issue. So I present here three examples. The first one is that you deploy the control services in one site, and you deploy compute nodes at the remote sites. A second example relies on segregation techniques like cells, which is a feature of Nova, or the multi-regions in OpenStack that share the same keystone service. The last example concerns the federated and brokering approaches on top of multiple OpenStack deployments. So the topic of this talk is not to give the pros and cons of such examples, of such deployments, but what is interesting is that we have to investigate many situations, many deployments and configuration. So two questions arise. The first one is how can we evaluate such critical services in a specific context of for computing, and how can we evaluate different deployment strategies? So for that, we need to propose a sandbox to help us to conduct various performance analysis of OpenStack. So this is the goal of EnOS. To fully understand the challenges addressed by EnOS, let's talk about performance evaluation in OpenStack. So to make performance evaluation in general, you need three things. The first one is an environment that you control and which is well known. So you want to know like the resource capacity, software versions, and the configurations. You need a way to collect different metrics from this system. So it can be CPU, RAM, and disk consumptions, but also service-specific metrics like the number of requests that are done on the database or the number of messages on the message queue, in the message queues. And you want to collect these metrics while you perform a specific and appropriate workload on your system. In OpenStack, performance evaluation can be done at two levels. The first one is at the control plane, which is at the level of OpenStack services like Nova, Neutron, MariaDB, or RabbitMQ, or at the data plane, which is the level of the resources deployed by OpenStack. So for instance, if you want to perform the, if you want to evaluate the performance of two Nova instances, like the network between two Nova instances. So why do we need performance evaluation in OpenStack? The first point is to validate configuration with regards to performance metrics, as illustrated in the introduction. So, for example, to find OpenStack bottlenecks in a specific context, like the one of fog computing, it is useful to help us to make the good design and architectural choices, and to find the impact of services settings. Furthermore, it can be used by developers in order to validate new features by checking that this new feature does not bring performance regressions. So we need to evaluate the performance for that. A point that is very important is that if you want to validate some stuff, you need your performance experimentation to be reproducible by others. So that would be a goal for us. So in OpenStack, there is the performance working group, which is in charge of defining and sharing information about the performance evaluation methodologies. So they share not only methodologies, but the labs and test beds that are used, that have been used, the test plans, and the results. So you can just have a look at the wiki of this working group. And they also develop some performance analysis tools like OS Profiler, which is the library in OpenStack to profile OpenStack calls, and OS Faults, which is the library to inject faults during a test on OpenStack, like stopping a service during the test. So I would like now to define 5 challenges that are related to OpenStack evaluations. The first one is that it is hard to compare different deployments of OpenStack. Why? Because first, we need to express different OpenStack configurations, so related to OpenStack release, the services that you want to deploy, and the settings of these services. It's also hard to manage multiple configurations of OpenStack and to switch between them. For example, it is the case when you want to compare a vanilla deployment. So vanilla is like OpenStack without any tweak. So you compare vanilla OpenStack with an OpenStack deployment where you have a custom version of Nova or a version of OpenStack where you activate a plugin or a feature in Neutron. Secondly, it is hard to reproduce experimental environment. So it is usually done by ad hoc solutions, but that prevents reproducibility. So what we want is to express a specific environment, like setting network constraints in our topology, like setting latency between nodes. And we want to be able to switch from a test bed to another one. More specifically, we want to reproduce an experiment from a test bed I to a test bed B. The third point is that it is hard to deploy an operable OpenStack, and we observe that as academics. Everybody is not DevOps, and what we want is to be able to deploy OpenStack without having to know all the stack. So it has to be easy to deploy it. It is also hard to, once you have deployed your environment and your OpenStack, it's hard to run benchmarks on it. Why? Because there are different types of benchmarks related to the control plane and the data plane. And sometimes you need to express complex benchmarking scenarios and you want to run them automatically. So it's a lot of things to manage. And finally, it is hard to collect and explore the results of your benchmark because there are many kinds of generated data, like logs from the services, configuration files from the services, and the metrics that you have recorded during the benchmark. It requires to manage a lot of different services, so services for monitoring your system, data stores to store, for example, the metrics, and data visualization in order to explore the data. And furthermore, you have to collect metrics from many, many nodes, so you don't want to manage it manually. You want to make it, you want it to be automated. So that's why we're looking for a software-defined approach to run these benchmarks. And it has to be driven by automated steps it has to be driven by automation for every steps of the experimentation. So now, let me introduce you EnOS and see how it can help you to solve all these issues. EnOS stands for Experimental Environment of OpenStack. Its purpose is to conduct performance analysis of OpenStack in a reproducible manner, so driven by automation, and for different testbeds. It can be a single virtual machine or a real large-scale testbed. We want to manage different network topologies. So for that, we want to support the traffic shaping and manage our and we want to run. EnOS enables you to run different kind of benchmarks with different OpenStack release and configuration and services configuration. So just to be clear, EnOS is meant to deploy ephemeral deployment of OpenStack, and it is not made to run OpenStack on production. It's just focused on performance analysis. So to that end, EnOS relies on Cola, which is an OpenStack project to deploy OpenStack services leveraging Ansible and Docker containers. So the Cola community has done an amazing work in order to enable people to build and deploy OpenStack services as Docker containers, and this for every release of OpenStack. Furthermore, it brings the ability to highly customize OpenStack deployments and services settings. So EnOS relies on 3 steps: deploy, bench, and backup. The deployment steps reads a deployment description file with all the information about the topology and the OpenStack configuration you want to deploy. So from the topology part, it says the experimental environment, so the machines. It can provision the machines, the monitoring tools, and set the network constraints of your topology. Furthermore, after that, it's deploy OpenStack according to the given configuration you provided. Second step is EnOS bench, which reads a description file on which is described the desired benchmark scenarios and run them on the deployed OpenStack. The final step is EnOS backup, which creates an archive with the generated data obtained from the benchmark, so the configuration files, the recorded metrics, and the logs for post-mortem analysis. So here you can see how which step solves the challenges we have listed previously. But now let's dig into the details of these steps. So I will present here 3 examples of topology description you can provide to EnOS. So this one is a very basic example. What we can see is we declare a node we want to control, so we want to use. So here I say I pick 2 nodes from cluster A. One node is one control node for the control services of OpenStack, one network node for the network services of OpenStack. And here I pick 50 compute nodes from the cluster B. So it is a very basic and straightforward example who can show you how we can describe the topology in EnOS. But we have more advanced thing. Like here, it's a more advanced description to show how we can isolate a specific service and play with its scalability. So in this advanced example, we isolated the Nova conductor from the control group, and we ask for 5 nodes on which we are deploying Nova conductor, so 5 times. The last example shows you how to define network constraints in our desired topology. So to that end, it is possible to declare groups of nodes. So you can see here the group 1 and group 2. And after that, we can express some network constraints on this group. So here, for example, we can express the fact that we want a latency of 100 milliseconds between group 1 and group 2. So let's see now how it works under the hood. EnOS deploy OpenStack services of any kind of resource. And in our context, a resource is anything that is reachable by SSH, and on which we can deploy the Docker daemon, which is a dependency of Cola. So to manage resources, EnOS rely on the notion of provider. And provider describe the internal mechanism that enables EnOS to get the 2 nodes here and the 50 nodes there. And providers return the list of the IP address of each node in order to be used for the extra steps. After that, EnOS provision those nodes with the Docker daemon and install OpenStack using Cola. After OpenStack has been installed, there is we populate OpenStack with the bare necessities, so flavors, Cyrus image, and network configuration, and so, in order for the OpenStack deployment to be operable. The final step is to apply the network constraint on the nodes we picked, and we do that using Linux traffic control, so TC. In EnOS, there are different providers, which are represented here. We have Vagrant. We have also providers for real test bed, like Grid5K and Chameleon, and a provider for OpenStack itself. So once your environment is ready and the OpenStack is deployed, you can run 2 kinds of benchmark. So using Rally, we can do a benchmark on the control plane, and using Shaker, we can do benchmark. We can benchmark the data plane. Benchmark scenarios in Rally and Shakers are described using scenarios file, as you can see in this example. So here it's a Rally example where we apply the process of boot and list 100 times with a concurrency of 5. We support also OS Profiler, which is a profiling library of OpenStack. So you can just say activate it during your benchmark. And we provide a monitoring stack, which is composed of cAdvisor and cont'd in order to keep track of information like CPU, RAM, network consumption of all the nodes in real time. So once the benchmarks are finished, EnOS enables you to back up the generated data in a tarball. And you can have different type of results. So there are cross-grained results, like the Rally report. Also the Shaker reports for the data plane. It's backup also more fine-grained reports, like the one of OS Profiler. So you can see all the calls that are made in OpenStack and the time required for them. It backups also all the databases that store the monitoring metrics and that you can explore using services like Grafana. And also OpenStack logs and configuration file. So everything is registered and backed in a tarball, and can be used afterwards in order to make post-mortem analysis. So you can find more information in the documentation of EnOS. So now that we saw how EnOS works, let's have a look at some use cases of EnOS. The first use case was presented during the Barcelona summit for the Newton release. It was also the first stable release of EnOS. And it is a joint work between INRIA, Myrentis, and the performance working group. The goal of this work is to find out how OpenStack control plane behaves at scale. So when we say at scale, it's when we try to boot 1,000 compute nodes. And for that, the goals was to analyze the control plane at scale and to identify bottlenecks and to solve by identifying key service settings and service topology and the impact of the service topology to reach this goal of 1,000 compute nodes. So we identified two things. The first one is the key service settings that are required to reach the 100 nodes. So we had to increase the number of workers for specific services like Nova Conductor and Neutron Server. We had to increase the maximum number of connections for database and message bus. But there are also some architectural requirements, like we saw that Nova Scheduler is a critical service, and we need one Nova Scheduler for 100 compute nodes deployed. What is interesting is that this leveraged the fact that EnOS is able to analyze the control plane using Rally to identify bottlenecks. And we were able to change easily some settings thanks to Cola and to redeploy it and check the impact of the changes on the settings and on the topology to reach this goal of 1,000 nodes. So someone asked me on Monday, because this was done with the Mikata release of OpenStack. He asked me if it was possible to do it again today. So obviously, EnOS is really made for that. You just have to take all the thing that was done for this experimentation, change the line of the OpenStack release, and we can reproduce all the experimentation very easily. So the second use case was presented during the Boston Summit for the Okata release. This is a joint work between INRIA and the University of Chicago. It's a first step in the evaluation of OpenStack for fog and edge computing. More precisely, it deals with the evaluation of OpenStack control plane and data plane in a WAN-wide infrastructure. So it means, as you can see on this figure, that a significant amount of latency is applied on the network links between the control plane and between the control node and the compute node. An important consideration of this work is that the validation of the results on two different test beds, so Grid5K and Chameleon. Grid5K is a French national test bed dedicated to research experimentations, and Chameleon is a similar test bed operated by OpenStack services like Blazar and Ironic in America. Both test beds provide hundreds of bare metal nodes, which is really important when you want to evaluate the performance, since the machines are dedicated to us. So this experimentation showed that latency has an impact of the completion time of operation at the control plane, but it also has an impact, a significant impact on the data plane. More precisely, we show that the response time between VM was very impacted when these VMs are set in different networks. Why that? It's because VMs of different networks need to fetch the routes, which are at the Neutron server, which is in the control node. So to solve this problem, it required to activate a feature of Neutron, which is called DVR, which solved the problem. And to solve it in EnOS, it just needs to add a single line in the configuration file. So thanks to EnOS, we had the support for different benchmarking tools, so Rally, Shaker, and OS Profiler to analyze this experimentation. We were able to reproduce the same experimentation on 2 test beds, so Grid 5K, which required a special provider, and Chameleon, which required the OpenStack provider of EnOS. Furthermore, we leveraged here the fact that EnOS supports traffic shaping in order to simulate this WAN-wide infrastructure. Further experimentation has been done with EnOS. So, for example, FBK, which is a research center in Italy, has used EnOS to deploy OpenStack in order to evaluate workload migration in fog infrastructure. And also the FedFire project, so it's a European project working on the Federation of Testbed for research experimentations. So they used EnOS in order to conduct comparison between OpenStack and OpenNebula. So let's have a look at the future works and conclusion. So for the future work, what we plan to do is the evaluation of critical OpenStack services in a massively distributed context. So this is a job with the FMDC SIG. So first, the message bus service. We want to see some alternatives like 0MQ and Cupid. And this is ongoing work with Orange, Red Hat, and INRIA. Basically, because Cupid provides now an MQP router to interconnect MQP endpoints in a distributed manner, so we need to evaluate these alternatives. And for now, we have defined the test plans, which is available as part of the performance working group documentation. The second thing we want to do is to evaluate alternatives for databases, more particularly on new SQL paradigm. So this is ongoing work with Cockroach Labs. Since Cockroach claims to bring scalability while providing an SQL API. So for now, we had a proof of concept based on Keystone. But it's just ongoing work. And the results are expected to be presented for the Vancouver Summit. OK, so just for conclude this talk, so EnOS is able to manage experimental environments for conducting OpenStack performance analysis by automating each step of the deployment of the experimentation workflow, so setting the experimental environment, deploying a highly customizable OpenStack configuration by running automatically the benchmarks and collecting automatically all the generated data for real-time and post-mortem analysis. A huge advantage of EnOS is that it is based on a software-defined approach. So everything is described in a configuration file. So it can be the topology, the OpenStack tuning, and the benchmark scenarios. Furthermore, we put forward the fact that all the experimentation are reproducible, which help us to validate the evaluations. And we give many providers to allow that. So EnOS has been used to conduct rigorous experiments. We saw the large scale, the WAN-wide, and we will see the evaluation of critical services in massively distributed situation for the message bus and database. And you can easily reproduce all this experimentation or tune them on your own infrastructure. So you can either use the existing provider, Vagrant, OpenStack, or for other testbed, or you can create your own, which requires only 500 line of code. So and you can easily tune your own OpenStack deployments since Scala enables it. So you can define the different release of what we do, so updated service of OpenStack, and use service features. So that's all for me. I would be glad to answer your questions. Yeah. I think, yeah, okay. Sure. You just need to provide the credential, and to the credential to EnOS, and it will. You can just execute the command EnOS bench. So that could work. Yes. Yeah.
The workload on your compute nodes and the network traffic, that's a generic benchmark, or is that customizable?
Yeah, so it's so the workloads are generated by Rally or by Shaker. So as soon as if it's possible to manage to personalize it in both projects, you can exploit it in EnOS. Yes.
Have you performed this OpenStack version and commercial releases of OpenStack?
Sorry.
Have you performed this evaluation for any commercial OpenStack?
No. You think about the distribution of OpenStack? No, not yet. We are using upstream version of OpenStack. But would you be interested in using that?
Yeah, sure. Actually, I also know that I'm working in the engineering community. They're also working on some, they call Yastic and Dovetail. They're working on some performance testing, but they would like to have them work also on some commercial products.
Yeah.
So commercial products might be more to, but this would make sense.
Okay. Yeah. Maybe we can discuss about it. Yeah. Okay. Other questions? Yeah.
Any further process regarding data automation for finding out regression? For example, you say that you collect data, but you don't mention in detail the process of finding out regression.
Sorry, I don't get the question. Can you please?
You say you collect data.
Yeah. Mm-hmm.
And you maybe use this data for finding regression.
Yeah.
Do you have automated the process in EnOS, or you do manual analysis on collected data, or do you think extending using a pipeline?
Yeah, that is an interesting question. That would be a very good way to improve EnOS, because for now it's manual verification of that. But you can easily exploit the data and compare them with some tools, or it should be a nice feature for next version of EnOS. Yeah, definitely. Other questions? Okay, so thank you.